welcome back once again, and this time we are going to talk about the adder circuit. Specifically, we'll talk about half adder first. So here is a block diagram of a half adder circuit. So as you can see, it has got two inputs A and B and two outputs labeled as sum and the carry. So we'll see in a moment why it is called as half adder. So let's say you have A and B, two inputs. Each can have logic 0 or logic 1 value. So obviously there are two inputs, so there are four possible input combinations: 0, 0, 0, 1, 1, 0, and 1, 1. And accordingly, these two columns say sum and carry will be produced. So for example, when you add A and B, which are both logic 0, the sum is 0 and the carry is also 0. When A and B are 0 and 1 respectively, when you make their binary addition, the sum is 1 and carry is 0. When A is logic 1 and B is logic 0, the binary addition produces a sum equal to 1 and carry is 0. However, look at the last case. When you have A and B both are 1, then the binary addition makes sum equal to 0. However, there is this carry generated. So if this carry generated is not being taken care of, or it is not being fed into a subsequent adding circuit, then it is. So if this carry generated is not being taken care of, then it is called as half addition. So for example, let's say you have A and B, which are 4 bits number each. This is 1, 2, 3, 4, LSB, least significant bit in number A, and 1 here is the most significant bit. For B also, this is LSB, and for this one is the MSB. Now we start the addition of individual bits starting with 0, 0. Both A and B have the values of logic 0. Sum here, the binary addition here gives sum equal to 0. Obviously, there is no carry. Then both A and B are 1 each. Addition of them is sum equal to 0. However, the carry gets generated. So this is basically 1, 1 is this combination 1, 1. Sum is 0 and the carry got generated. So now if you have another adder circuit, then this carry is sitting now right on top of here, and then 1 and 1. Again, you make the addition and sum is 0, again gets carry generated. So the carry got generated here, and now we 1 plus 1 again in binary. You have sum equal to 0 and the carry gets generated here. So as long as your carry generated from the previous addition is being taken care of, then you can call it as a full addition. However, if it is not the case, then it is half adder. For example, you stop right over here, you make the addition and you don't have any further circuitry, then it is called as half adder. So we'll see in a moment how the full adder is taking care of the carry generated. So this is how you see that in the case of this 4-bit numbers. Okay. So let us move forward. Once you have this table, what you can do is you need to generate a logic circuit to implement this half-adder logic. So this is the two variable K map that we want to produce for two outputs, sum and the carry. So A and B, 0, 1, 0, 1. So if you look at the sum column, for this combination A is 0, B is 1, A is 1 and B is 0, your sum is 1 here. So what you make here, A is 0, B is 1, you mark the variable mean term here. And when A is 1, B is 1, you mark the mean term right over here. So once that is done, you can see that these ones are not adjacent ones, so they cannot be clubbed together. Rather, they are marked individually. And once that are marked, so this mean term, the product term is A bar B, and the product term out of this is A B bar. So that's why sum equal to A bar B or A B bar. In short, this is A XOR B logic. So we need a two input XOR logic gate. For the carry, you see that the carry in the last row, both A and B are 1, the carry is marked as 1. So this is the mean term. We see here A, B are both 1 and this mean term has been marked. So we got the one product term carry equal to AB. So once we get the expression sum and carry, is time, we see that we have got the half adder circuit where the A and B are the two inputs, sum is equal to A XOR B, and carry is A and B. So A and B both inputs are coming from here. So this is how a simple half adder circuit that will make the additions right over shown over here. However, once the carry gets generated, let's say from this example, this half adder circuit is not taking into account the carry generated from the previous addition. That's why it is called as half adder. Now, full adder, it should take into account the carry generated from the previous addition, and we'll see how it does that. So what it takes is that instead of two inputs, now it is going to receive a third input. So this third input C in is basically indicating the carry generated from the previous addition is being fed into the circuit. That's why it is called as full adder, and now it has got three inputs. Obviously, it will have sum and the C out. That is the sum and the carry out are its outputs. So here is the truth table. So you see that the truth table, there are sum and the carry, both columns, and the mean terms produced are marked individually for the sum, and the mean term produced are marked individually for the carry. So since there are three inputs A, B, C, there are 8 possible combination of the inputs. Now you add each of these bits individually, and you can observe for which combination of the inputs the sum and carry are marked as 1. So for example, when you add 0, 0, 0, sum is 0, carry is 0. When you have 0, 0, 1, the binary addition of these three bits produces sum equal to 1, carry is 0. Binary addition of 0, 1, 0, sum is equal to 1, carry is 0. However, look at this. When A, B, C are 0, 1, 1 respectively, here is the sum, binary sum is 0. However, the carry gets generated. Now, if you have these three combinations, 1, 0, 0, then sum is 1, carry is 0. Similarly, you can analyze for all other combination. For the last combination, when A, B, C, both all are 1, the sum is 1 and the carry is also 1. So now since we have marked these mean terms for the sum and carry outputs, what we can do is get a K-map for the sum and the carry. For example, this is the three variable K-map for the sum output. So A is marked here, B, C are marked here. So obviously B, C have four combinations, 0, 0, 0, 1, 1, 1, 1, 0, and A can be 0 or 1. Once that is done, we have to look into the table 1, 2, 4, and 7. For these rows, we have main terms marked as 1. So that's what we have exactly done. This is 1, this is 2, this is 4, and this is 7. Now all these ones after marking, they cannot be paired together. They have been individually marked. So we got the four main terms out of this table. So first one is A bar, B bar, C, right? Sum is equal to A bar, B bar, C. Or second mean term is A bar, B, C bar, A bar, B, C bar. Third mean term is A, B bar, C bar, A, B bar, C bar. And the fourth mean term is A, B, C in. That is how we get the full expression of this. Now, if you see carefully and try to minimize this expression, this is nothing but sum is equal to A XOR B XOR C in. That's how we got the first expression. What we can do now is get the another K map for the C out column. So here we have to mark the mean terms in row 3, 5, 6, and 7. That's what we have done. 3, 4, 6, and 7. Once we have marked, we can see clear pairing of all these ones. These two ones can be clubbed together, these two ones can be clubbed together, and these two ones can be clubbed together. Once that is done, we see that the blue indicates the mean term produced BC, black indicates mean term produce AB, and the red indicates mean term produce AC. So these three product terms, so this is the C out expressions. After we get the sum and carry, it's time to implement the logic circuit. So what you do here, you have three inputs A, B, C, and right over for the XOR output, you get the sum equal to A XOR B here. That goes as an input here. The third input is coming right from here. Finally, at this output of the second XOR, you have this expression A XOR B XOR C. Similarly, for the C output, we need three NAND gates. So the first BC is being addressed by this NAND gate, then second is this NAND gate, and the third mean term is AC is this NAND gate. Once these three AND gates are produced right here, they can be clubbed together and fed to the OR gate. That's how you get carry out expression. So this is how we implemented full adder circuit using the K-maps, truth table, and the Boolean expression. So let us move forward. How about implementing the full adder using half adder? So for example, we'll use A and B are the two inputs of the half adder. It has two outputs, sum and carry. You use second half adder section. It has got two inputs, A and B. Outputs are sum and carry. Now we have to club these two half adder in such a way that it will implement the full adder circuit or full adder logic. So this is how we do it. So you see that the first half adder has been placed here, second half adder has been placed here, and we see that for the first half adder, A and B are its input. Now its outputs are sum and carry. So sum is A XOR B. We know that what sum it gives us. So this is what we have written, and its carry is A and B. This is also we know that the carry of a half adder is A and B. Now for the second half adder, the output of the first half adder goes as an input. That is sum equal to A XOR B becomes its input, and the second input of the second half adder is nothing but a carry generated from the previous addition of the bits from the first half adder stage. So this C in is basically its second input of this half adder, and this C in is coming if it is generated from the previous addition of this half adder circuit. Okay, and it's obviously it has got two outputs, sum equal to then A XOR B, which is this XOR C in, and the C out here or carry of this second adder will obviously the AND operation of these two inputs. So that is A XOR B and C in. This is how we get it. Once that is done, now look at this. The carry of the second half adder and the carry of the first half adder, they are the two product terms which can go to the OR operation, producing the final C out, which is this term or this term. So A XOR B and C in or AB. So output C out is equal to 1 when either this term is 1 or this term is 1. So this is how you can implement the full adder using two half adder and one OR gate. So now it's time to see the logic circuit. So this is the first half adder we have taken. A and B are its inputs. Sum is A XOR B, carry is A and B. We know that we use the two logic gates. Similarly, I use then second half adder, but now look, the output of the first half adder goes as one of the input to the second half adder's XOR logic, and its third input is coming from the C in. Remember, if the carry gets generated right here, that becomes the input right over here, and it has got sum and the carry are its two outputs. What I did here then, the output of this AND gate, that is the carry from the second half adder and the carry from the first half adder, they both come as an input to this OR gate, producing the C out. So finally, we see that you got the sum, which is A XOR B XOR C, and C out is A XOR B and C in or A B. So this is how the full adder circuit using two half adder will work. So if you take an example here, you will see that how this circuit will implement the full addition. Just have the A and B, let's say 1, 1. Then the sum here is 1. Carry here is 1. The C out is 1 because one of the input here is 1. And since you have XOR is 1, then C in got generated 1. So the output is 0 here. Sum is 0 because both inputs are 1. So this is how you actually can see that the full adder works, and hope you found this model useful. So hope you found this model useful. If you did so, share it with others for a wider reach. Stay tuned for more informative and engaging content like this. Till then, wish you happy learning.